was about to say. All right. Who didn't bring a laptop? I'm just curious. There's like, I'm not raising my hand. We are going to be doing a little bit of laptop work today. It's not the end of the world if you didn't bring your laptop, but the main reason for bringing your laptop is because we're going to have an example today where computing or constructing the shear and moment diagram using a purely graphical approach is going to be tough. And so I want to go back to doing the math a little bit. And so we're going to be using Excel, and I just like to integrate Excel whenever I can because your engineers and Excel should be your second fluent language at least. Okay, if not more, given our earlier discussion about Spanish and whatnot, if you can speak Spanish. Right. So attendance is up to date. Homework 5.2 is being graded. I'm hoping that this last shear and moment diagram assignment was easy. I'll tell you that I'm going to give you an assignment today that's going to be due Friday where you're going to be submitting an Excel spreadsheet instead of a written count. And I'll also tell you that the assignment is easier than what we're doing in class. But I would pay attention to the hints and I would pay attention to what you're doing on that assignment. Just parroting what we do in class and not paying attention to how the assignment is structured will probably cause more problems. But we'll get to that when we get there. Don't forget you have your first submittal for your project due on October 14th. Okay. I know I said I'd have the exam graded today. I'm sorry, it didn't happen. I need to get it off my desk at some point though, because I'm going to be having a statics exam coming up here soon. So we have 4 exams in there. So, okay, everybody gets code. All right. Okay. So keep in mind we are still using the same principles of how we relate load and shear and how we relate shear and moment. That if we have the loads, we can integrate them to get the shears. If we have the shears, we can integrate them to get the moments. Or the flip side. And actually today, we're going to use the flip side. We're going to use the derivative relationship, but we're going to use it more as a means of just as a gut check to make sure that what we did by hand actually makes sense. And you'll see that when we get into our example today. Same thing with our conclusions for our graphical approach. Now, what's going to be interesting today is that the loads that we're going to deal with are going to look like this. They're going to be linear loads, triangular loads. And so if you have a linear function and you integrate a linear function, you get a quadratic function, right? And then if you integrate a quadratic function, you get a cubic function, right? Okay. So what's going to get a little weird is, so remember how we construct the moment diagram. We construct the moment diagram by integrating the shear diagram. Well, that's all fine and good if the shear diagram is a bunch of rectangles and triangles. But what if it's not? What if the shear diagram is this parabola thing? It's going to be difficult to do that graphically, okay? So we're not going to do it graphically. We're going to do it a different way. But we're also not going to integrate it either. And you're probably thinking, well, if you're not going to integrate it, if you're not going to do it graphically, how are you going to do it? Don't worry, we'll see, okay? Now, if you remember last time, I said that I wanted to not have geometry be a problem. That we did this sort of geometry problem on the side, and then we did our example so that when we got to that geometry, suddenly the example wasn't so challenging. Remember that? We're gonna do the same thing here. Okay, so let me sort of explain what's going on here. So let's just assume for the sake of discussion that I had a beam, okay? Let's say I have a beam and it's, simply supported and I have a triangular load on it, okay? And this is 4 kips per foot. And then this distance is 35 feet, okay? Let's just say that's the case. Okay, and I cut a section, okay? So let's samurai sword or lightsaber right there, okay? And I cut a section at some distance X away from the support, okay? So remember, when you cut a section, what that means is that you're literally splitting the structure into two separate pieces, and you only consider what's on one side. So what I want to do is I want to erase all this and be left with this, okay? So I'm left with this, okay? And so if I cut that, I'm going to have an unknown shear, an unknown moment, okay? And so I guess my question is, this is a triangular load, right? Okay, so I'm going to collapse that into a point load, okay? So my question is, what is that point load? And then also, what is my moment arm? And these are geometry problems and algebra problems more than they are structural analysis problems. So I kind of want to do this first so that when we knock this out later, this part isn't challenging. Okay, so again, not really a shear and moment diagram issue as much as it is a geometry issue. So. Okay. Now, my goal is to do the following. Okay, my goal is to figure out what this F force is and what this D force is, but I want to figure it out in terms of X. Okay, so I want D to be some, quantity in terms of X. I want F to be some quantity in terms of X. So let's see if we can do an easy one first. Okay, so help me out. Let's take D. Okay, does anybody have an idea of what this term D would be? 1/3 X. 1/3 what?
X.
X. Okay, so I agree. That's right. So that D is X over 3. Now, by the way, why is it X over 3?
Coming from the right, not the left side.
But it's X, yes, but it's X over 3 because the shape is a what?
Triangle.
It's a triangle. So what you're telling me is that if this was a rectangle, it wouldn't be X over 3, right? Mm-hmm. Right? So when you do your homework assignment and you put X over 3, I'm going to ask you to take your hand up and no. Keep that in mind. Okay. All right. So let's see if we can figure out a formula for F. Okay. So let's just take a step back. How do we compute the area of a triangle? 1/2 what?
Base times height.
Base times height. Okay. So let's see if we can at least figure that part out. So would you agree that F is going to be 1/2 base times height? What is the base? X. Okay. Now the height we don't know yet. Okay, so I'm just going to call that H. Okay. But I would say that this dimension here is the height. Is it 4?
No.
No, it's not, right? It's not 4, okay? It would be 4 over here, but not there, okay? So let's see if we can come up with some observations. What would, at x equals 0, what would the height be? 0. What about at x equals 35? What would h be? 4. So I guess at x, h equals what? We need to figure out what h is in terms of x. Does that make sense? Okay. So here's what I'm going to do. I'm going to say that 4 is to 35 as h is to x, or h is 4x over 35. Now, Does that comport with this right here? What happens if x equals 0? What do we get for h?
0.
What happens if x equals 35? What do we get for h?
4.
So does that comport? Is this a linear relationship, right? Like if x was 17 and a half, h would be 2, right? Make sense? So what I'm saying is now we can say 1/2 x times that, or that. Okay? So what I'm saying is now we have a distance in a moment arm in terms of x, and now we have the force written in terms of x, right? I mean, does this make sense? Let me ask you a question. What if x equals 0? What is the force? 0, right? But what would that mean? Let's take a step back. What would it mean for x to be 0? It would mean that I'm cutting the section right there, right? If I cut the section like right here and look to the left, there's nothing there, right? Somebody help me out. What if x is 35? What is f? Somebody break out the Casio FX115ES Plus or similar scientific calculator. If x is 35, well, can we do this in our head? We have 35 squared over 35, so 35 times 2 is 70. Okay, what is the area of the entire triangle? 4 times 35 over 2, which is 70. So if x is 35, that's the whole triangle, right? What I'm saying is as we cut a section and move this way, the area changes. What is the area? It's mapped by that function there. Does that make sense? I don't want that to be a challenge. Okay? Make sense? All right, any questions? All right, if that's the case, then what I want to do now is focus on this. So now I want to determine the shear and moment diagram for this beam. Okay, so I have a beam that is subjected to a triangular load. I made the numbers a little softer. I've got 2 and 30. I did a 30, so because it, a third, it would divide up evenly into thirds. And I have, this goes to 2 kips per foot. So I want to find the reactions, and then I want to plot the shear diagram and plot the moment diagram. Now we're going to take a stab at maybe trying to figure out what the moment diagram and the shear diagram should look like. We're not going to get all the way there, but we're going to get pretty close. Okay? So, let's see. All right, now, the other thing that I'll mention is that there is a coordinate system there. I put an XY coordinate system. I'm not going to need that for reactions, but I will take a look at that using that a little later. Okay, so far so good? Okay. All right, so maybe, so we need to compute reactions. Maybe what I need to do is take that triangular load and collapse it into a single point load. How much would, if I collapse it into a point load, how much would it be? 30 kips. And how far away from A would it be?
20 feet.
20 feet. So okay. All right. So, oh goodness, there's all these pop-ups. Okay. So maybe what I'll do now is I'll sum moments at A. I mean, this part should be easy, right? I'm hoping this is pretty straightforward. So I've got 30 times 20, by times 30, right? Everybody with me on that? That should be pretty easy, right? So So 600. And then is that fair? That should be fair, right? So that makes this 20. So if that's 20, what's the other one going to be? 10. So here's what I'll do. I'll just say okay. All right, how are we doing? So far, so good? Okay. So now remember, when we construct the shear diagram, do we use this 30 kip load or do we use the triangular load?
Triangle.
Remember, exactly right. Remember, this 30 kip load was just a mathematical abstraction that we created to make the computation of the support reactions easy. That's not what's actually going on the beam. What's actually going on is a linearly increasing load. Make sense? Okay, so okay. Now let's see if we can reason our way through what this is going to look like. Okay, so this is a pickle. This is a challenge. Okay, because now help me out. Oh, sorry. We're going to start at 0. So, all right. What's the first thing that we're going to do?
Go up 10.
Go up 10. Okay. Okay. All right. So up 10. Now, how much total load is on the beam between here and here?
30 kips.
30 kips. Okay. So let's just sort of ignore what's going on here, at least for now, and say that if I'm at 10 and I go down 30, what am I going to be at?
Negative 20.
-20, and then this is going to bring me back up to 0, right? The question is, what happens between here and here, okay? This is a line, right? If I integrate a line, I get a
Quadratic.
quadratic. So it's going to be a parabola from here to here, right? And is that parabola going to be open upwards or downwards?
Downward.
Down. Because the load's going down, right? So if I start at 10, got to go to -20, downward parabola, maybe this? Right? Okay. All right, let's see. Now we need to integrate that, right? Dang it. That's hard. I mean, I'm being facetious, but not really, right? I have to integrate this nonlinear function, okay? Now, I do know, now let's have some common sense here, okay? I do know that this is positive and that's negative, right? I'm also going to say that there are no other moments or other functions, so I'm going to say that these two areas have to equal one another, right? Okay? Now, if I have a quadratic shear diagram, that means I'm going to have a cubic moment diagram, okay? And I have 0 shear right here. So 0 shear should be where the moment is maximized. So I'm going to start at 0, go up to some value, which I don't really know, come back down to 0, and it's probably going to look, I don't know, remember that whole lot to a little thing? Lot to a little, little to a lot. So lot of slope to a little slope to a lot of slope. It's probably going to look, I don't know, something about like that. But that's not a whole lot of specificity, is it?
No.
Not a whole lot of value, right? So now what? What do I do to actually get something I can sink my teeth into, some actual quantitative data, okay? I could break out some calculus, which we will indirectly use some calculus here in a bit to verify our answers, but I'm going to break out the secret weapon of structural engineering, which is the samurai sword, or the lightsaber if I happen to be a sci-fi fan. And what I'm going to do is I'm going to handle this a little differently. Instead, what I'm going to do, I'm going to cut a section. And I'm going to cut a section at a specific distance away from this support. How far away? X away. I'm going to cut a distance X away from this support, and I'm going to see if I can write some functions. Okay? So, let's do that. Okay? Everybody get all this so far? Okay, so let's see if we can write some shear and moment functions. Okay? Let's cut a section at X looking left. So let's see. Remind me, what was this reaction right here? 10 kips, right? There's shear and moment. Okay. This dimension right here is X. Okay. We're going to collapse this, triangular load into a force and a moment arm. Now, if this is X, what's this moment arm? X over 3. Okay? Now, what about this force? Okay, well, let's see. Okay. This is 30 feet. This is 2 kips per foot. Okay. And what we did is cut a section at some distance X. And what I'm interested in is H, right? So 2 is to 30 as h is to x. Is that a fair statement? So therefore, two x over 30 or x over 15. And by the way, I'll just go ahead and tell you, I'm probably going to be a little fast and loose with documenting units because every force unit is going to be in kips, every distance unit is going to be in feet. So I'll let the context take care of that. So therefore, F is going to be 1/2 base times height, or x squared over 30. Is that a fair point? So how are we doing so far on the belief? Everybody believing me on this? So how do I solve for shear in moment? How do I do that? There you go. Some moment's about to cut, some forces in the y direction. So let's sum forces in the y direction. So no different than what I've been doing before. What do I have going up on this beam?
10 kips.
10 kips, okay? I'll just be honest, I'm just going to call it 10. What do I have going down?
V and x squared over 30.
Well, I can do better than that. Okay, let me move this over just a little bit so I don't run out of space. So is V is that V? Is that V? Let me make that a little neater. Okay. All right. I think that's important. I'm going to put that on the board. I'm going to say that V I think that's important. Now, what about the moment? How do I do that? As you said, some moment's about to cut. Let's do that. Let's see what happens. So tell me what to write. What do I do with this 10 kips? What do I do?
Ignore it.
Huh?
Oh, never mind. Wrong thing.
10x on what side, left or right?
Left.
Left. 10x goes right here. What about on the other side? What do I do with this f, this x squared over 30? Multiply by x over 3 on this side, right? So I should have x squared over 30 times x over 3, right? And then I should also have a moment right there, right? I don't need to worry about the v because it goes right through the section cut, right? So let's do some algebra here. So I got 10x equals m plus, okay, what is that? So I have x squared over 30 times x over 3.
X cubed over 90.
X cubed over 90. I get this feeling that that's important too, so I'm going to write that down. So m okay, everybody with me on that? I can't, now hold on. Did I do this right? Did I get this right? Is there a way of checking that? Because I can't seem to like shake this idea that there's something relating these two.
Take the integral of v against the derivative.
Or the derivative, right? So that's a good question. Let's discuss that a little bit. So you said take the integral, you said take the derivative. I think it's better when you're doing this type of check to take the derivative. Why? Because if I take the integral, I'm going to get a pile of junk plus c. But if I take the derivative, I don't have to worry about that. So what is the derivative of this? Well, it's the derivative of that, right? So factor the 10 out. What's the derivative of x?
1.
Minus, factor out the 190. What's the derivative of x cubed?
3x squared.
So I get 10 minus x squared over 30. It's almost like the derivative of moment equals the shear. By golly gosh gee. So I'll just put a note. So what do I do with these equations? What do I do with them? I do what any engineer would do. I break out the wonderful world of Excel. Okay. All right. Let's look at some Excel. So what I'm going to do is I'm going to set up 3 columns. I'm going to set an X column up. We'll say that's going to be in feet. We're going to do that. Okay? How long was this beam, by the way? 30 feet. So we'll say 0, 1, and then remember you can highlight this, put your cursor over that bottom corner until you get the solid black crosshair. We're going to drag until we get to 30. Y'all remember that? Okay. Okay. So what is shear? Shear is what? 10 minus x squared over 30. So equals 10 minus that squared over 30. Everybody see that? Okay, we'll press enter. And then remember, I can go to the little plus sign on the bottom right and double click. Boom. And I get this mess. Does this mess look right?
Yeah.
Well, what do I get at the very top? What do I get at the very bottom? Negative 20, right? That's what I wanted, right? Let's look at the picture, because I'm a pictures guy. Do y'all know how to quickly plot X and Y data like this? So you can highlight, everybody watch up here. So you can highlight both columns. So see how I've highlighted both columns? And just go to insert and just do like that one. And then it'll do the plot for you. Does that look right? That kind of looks like the picture we drew earlier, right? Now, no self-respecting engineer is going to just take the Excel plot that it gives you without doing a little bit of work to pretty it up a bit. Let's do some work to pretty this up a little bit. All right, so I'm going to right-click this x-axis. I'm going to hit Format Axis. The axis goes from 0 to 30. All right, because we don't need any trail over. Let's take the labels, put them on the bottom so that I can actually read them. Okay? And yes?
How did you cover this again?
This equation right here. So 10 minus like that column over 30. I'll pull it up here in a second. And by the way, keep in mind, all the hyper-specific Excel stuff, I'm recording this, so if you miss something, don't worry, it'll go on the playlist. All right, let's take this and put some titles on it. Call that distance across beam. Let's call that shear. Call this the shear diagram. And I'm going to, just so everybody can kind of see this in the class on the screen, I'm going to take the axes, I'm going to make them a little darker so you can see where the 0 line is. Maybe I'll make these grid lines a little lighter. Okay. Is that making sense? Something that's kind of interesting that that might seem like a mistake, but it's not. Where does the shear equal 0? What does it look like it equals 0?
It's like 17 and a half.
About 15, 20, maybe like 17-ish.
Yeah.
Doesn't it seem like it should be 20? Because the 2/3 over, it seems like, but it's not. And it's correct that it's not. And we'll see that here in a bit. Okay. Everybody good? All right, watch this. Okay, so here's my function for shear, right? 10 minus that squared over 30. Now, how am I going to do moment? I'm going to do this, right? 10x minus that squared over 90. Or, sorry, that cubed over 90. So equals 10 times the x column minus the x column cubed over 90. Okay. And then double click that. So are these values making sense? What do we get at x equals 30? 0. All right, now watch this. I want everybody's eyes up here. Watch me. Don't work hard, work smart. So watch this. What I'm going to do, I'm going to take this entire chart. I'm going to copy and paste it. Now watch. See this right here? I'm going to drag over. So, and all we'll do is just retitle this moment, retitle this axis. And make this as foot kips. Okay, so we'll take that, put it there, take that, put it there. Boom. All lined up. Does the moment diagram kind of look like what we said it would? Pretty good, right? Okay. Does the place where shear equals 0 align with where the maximum moment is? It should, right? Because of our derivative integral relationship. Let's also look at some numbers here. So let's look at the shear column. Where does shear equal 0? Well, at x equals 17, shear is about 0.366. At 18, it's negative 0.8. So shear equals 0 somewhere in the middle right here, right? And then what about maximum moment? Look at the moments. You can see that the moments maximize right here, and it's about 115 and some change, right? Now, this is only doing discrete calculations every foot. It's not the exact maximum or the exact, minimum. Where is the maximum moment? It is where shear equals 0, right? Everybody with me on that? So let's do some calculations back in our notebook, okay? Let's see if we can math this thing out. Find the point where shear equals 0. What is shear? Shear is 10 x squared over 30. So what am I going to do? Add x squared over 30 to both sides. Then what? You tell me. You know how to do this. How am I going to solve for x? Multiply by 30, so I'm going to get x squared equals 300. What is the square root of 300, by the way?
17.32.
And we'll say feet, because it is feet. Does that comport with what we just plotted? Looks about right to me, doesn't it? So how do I find the maximum moment? How do I do that?
Plug that into the moment.
Plug that in to this. So and so if you want, you could say square root of 300 if you want to keep it hyper accurate. So what is M max? We'll say to the nearest, I don't know, 2 decimal places.
115.47.
Crazy, isn't it? Pretty slick, isn't it? And again, does that comport? Well, what do we got here? We have where shear equals 0, we calculated 17.32. That's 17, that's 18. Sounds about right. Maximum moment, 115.47. This is 115.4. This is 115.2. It should be a little higher than that. It is. Well, by golly gosh, gee. Excel tricks too, isn't it awesome? Fun stuff, right? Okay, so here's the thing. I'm giving you a homework assignment on this where I want you to do this, but it is not for a triangular load. It is for a uniformly distributed load. So it should be easier. But do not just blindly start doing everything that we did in here because we were looking at a triangular load. It's not a triangular load. It's a rectangular load. So keep that in mind. Okay? Sound good? All right. I'm going to pull up the code. That's all I got, everybody. I will see you all on Friday.